Hello, this is the Algebraic Curves course, which is really a first course in algebraic geometry. So our subjects are going to be curves living in projective planes, in fact, two-dimensional projective spaces, primarily over the complex numbers, but also making sense over other fields. I'm going to spend the first 3 lectures talking just about projective geometry before we explain what algebraic curves are. So projective spaces are a kind of space. Lectures 1 to 3 will be about projective geometry. So some reading for this would be the Hitchin lecture notes, section 1. Now I want to start off by telling you what projective spaces are. So these are some kind of generalizations of the usual spaces R to the n, which you're used to doing geometry in. So let's talk about these. So this is some kind of generalization of, or way of doing geometry using kind of linear algebra broadly. So we're going to work with vector spaces over some fields. So my field is going to be called F. Let F be a field. So usually for us, F would be the real numbers or the complex numbers, but you can also take the field Fp for P prime and so on. Okay, so let's suppose V is a finite dimensional vector space over our field F. Normally the dimension will be n plus 1. And we define the projective space P of V associated to V to be the set of one-dimensional vector subspaces of big V. So this is a place where our geometry is going to happen, and I hope that by the end of the lecture you'll have some idea of why this is a sensible idea. Okay, so let's have some more notation. For each non-zero vector little v in big V, we write square brackets little v is the set of all multiples of V, so that's all lambda times V for lambda in our field F. So then that's a point in P of V. This is V is a basis vector for that one-dimensional vector space, and P of V is exactly the set of all points square brackets V for little v, a non-zero vector in big V. And the point does not determine the vector little v uniquely. In fact, we have brackets V is brackets W if and only if V is lambda times W for some lambda in your field, but lambda has to be non-zero. So lambda a non-zero element of the field. So we can also write P of v is, well, v take away 0, brackets, divided by, well, f star. So by f star, I mean the field take away 0 as a group under multiplication. And the group action on this thing is just rescaling multiplication by lambda. So something to note about that is, let's say this is a real or complex vector space. Then this is a quotient of, well, a subset of a real or complex vector space. That becomes a topological space. This thing has a quotient topology. Okay, so over R or C, this thing becomes a topological space. It's actually a very nice topological space. It is compact in Hausdorff. It's something called a real or a complex manifold, which is part of a very important story in geometry, which you may get to study later on in your degree. Anyway, we won't talk about that now. So we define the dimension of P of v to be the dimension of v minus 1. So the reason for the minus 1 is that, well, that thing here has the dimension of v, but dividing by this one-dimensional group reduces dimension by 1. So if dimension of P of v is 0, well, in that case, P of v is a point, because there's only one-dimensional vector there is only one-dimensional subspace of a one-dimensional vector space, which is the whole thing. So dimension P of v is 1. Then P of v is what's called a projective line. If dimension of P of v is 2, then P of v is a projective plane. So projective planes are going to be particularly important in this course, because we're going to define algebraic curves to be special subsets of projective planes, defined as the zeros of some polynomial. Okay, so for example, P of R3, well, you can take that as R3 take away 0 divided by non-zero reals. Another way of doing that would be to say it's you could just take the unit vectors in R3 and divide by the group preserving them, which is plus or minus 1. This is clearly a two-dimensional object. P of R2 is the circle divided by plus or minus 1, which again is one-dimensional. So that's why subtracting 1 is a good thing to do. Okay. Next, let's suppose that big U is a vector subspace of our vector space big V. So a common notation for this is U less than or equal to V. So that's slightly stronger than saying U is a subset of V. It's a subset of V, which is also a vector subspace. Then, well, it's just kind of obvious that P of U is a subset of P of V, because a one-dimensional vector subspace of U is also a one-dimensional vector subspace of V, so a point in there is a point in there. And we say that P of U is a projective linear subspace of P of V. So that this is the first. Okay, so first of all, I've defined projective spaces P of V as a set. Now we know that they have a bunch of distinguished subsets, the projective linear subspaces. And they're things we can do geometry with. So, well, a linear subspace P of U with dimension of P of U is 1 is called a projective line in P of V. And, well, also a projective linear subspace P of U with dimension of P of U is equal to dimension of P of V minus 1. So something with dimension 1 less than the whole thing. This is called a hyperplane. Okay, so you should be seeing this as some kind of geometry, generalization of geometry in R2 and R3. In R2 and R3 we have notions of straight line. The projective lines in projective spaces are kind of direct generalizations of lines in R2 and R3, as we'll see. And some common notation will be Rp to the n, in black bold, is a projective space of R to the n plus 1. Cp to the n is a projective space of C to the n plus 1 when our field is complex numbers. And, well, Pn or P lower n for n-dimensional projective space if you're not specifying your field. So I prefer superscripts, but I think the Hitchin writes P lower n in his notes. All right. Let's now talk about different notions of coordinates. So I have a section on coordinates on projective space. So let's take V to be a finite dimensional vector space over our field F. Let's say dimension is n plus 1. And let's choose a basis. So things look nicer notationally if we start numbering from 0. So the basis will be V0, V1 up to Vn for V. So then, well, every little v and big V can be written uniquely as V is a sum from I is 0 up to n of xi vi for xi in your field F. So let's make a definition. Well, if we let x0 in xn in our field to be not all 0. Then we're going to write square brackets x0 up to xn for the point P is brackets x0 v0 plus xn vn in P of v. So it's important to use square brackets here because we're going to use round brackets to mean something different. Okay, so, well, every point in P of v can be written this way. So we call square brackets x0 up to xn homogeneous coordinates. For the point P. So once we choose a basis for v, we have this notion of coordinates for points in P of v. So one thing to note is that brackets x0 up to xn and brackets y0 up to yn represent the same point P, if and only if, well, the vectors x0 v0 plus up to xn vn and y0 v0 plus up to yn vn, if these are proportional, so that is if and only if yj is lambda times xj for some lambda in your field, take away 0, and all j. Okay, so homogeneous coordinates of a point are not unique, well, except over the field with two elements, but can always be rescaled. By some lambda in your field, take away 0. So the word homogeneous is to do with rescalings. So you might talk about a homogeneous polynomial to be one which behaves in a certain way when you multiply all the coordinates in the polynomial by a constant. Okay, so that's our first notion of coordinates. We'll have a second notion which is called inhomogeneous coordinates. Okay, well, so now let P of v be a projective space of dimension n with homogeneous coordinates square brackets x0 up to xn, and let u0 be the subset of points x0 up to xn in P of v with x0 non-zero. And then for a point in here, we can put yj is xj divided by x0, for j is 1 to n. And then x0, x1 up to xn is equal to the point 1, comma y1 to yn. Just rescaling by x0 inverse. Okay. So we represent the point square brackets 1, comma y1 to yn in P of v by round brackets y1 up to yn without the leading one. And we say that these round brackets y1 up to yn are inhomogeneous coordinates. So homogeneous coordinates are kind of compatible with rescalings of the vectors or the numbers. Inhomogeneous coordinates are not. The inhomogeneous coordinates on the subset u0 in P of v, which is not the whole of P of v. So inhomogeneous coordinates are coordinates of the usual sort. So not like homogeneous coordinates. And by the usual sort, I mean well, each n tuple of numbers determines a unique point. So they give a one-to-one correspondence. Between our subset u0, it's an open subset if you're doing topology, and the vector space f to the n. And they are defined only on a subset u0 in P of v, because if x0 is 0, you can't divide by it. Okay, so now actually we can start to get a bit more intuition as to what projective spaces look like. Because we've got a projective space P of v. Inside it we've got a large subset which looks like a vector space f to the n. We can say what's the rest of P of v look like. So now P of v take away u0 is the set of points brackets x0, x1 to xn with x0 equals 0. So this is a projective subspace P of w, where w is the vector subspace of v, is the vector subspace spanned by the basis vectors v1 to vn, but not v0. So that P of w is a projective space of dimension n minus 1, which is 1 less than dimension of w. OK, so P of v is f to the n disjoint union P of w. So in particular, let's say complex projective space Cpn. You can identify it with a copy of C to the n and a copy of Cpn minus 1. So that's your subset U0, where the x0 coordinate is non-zero. That's your subset where the x0 coordinate is 0. And similarly, real projective space Rpn is an r to the n together with a Rpn minus 1. In general, P to the n is f to the n together with a Pn minus 1. And of course, you can iterate. So then, by induction, you could write Cpn as a copy of C to the n together with a copy of C to the n minus 1 together with all the way down to the C to the 0, which is a point. We think of the Cpn minus 1 in Cpn as the points at infinity in C to the n. OK, so Cpn is a kind of, if we're doing things with topologies, this is actually a compactification of C to the n. So C to the n is a non-compact topological space. We're adding some points, some extra points, forming a copy of Cpn minus 1 on, which makes Cpn into a compact topological space. And to get to a point here, you can take a limit of points in C to the n which are going off to infinity in some direction. So really Cpn minus 1 is parameterizing the complex directions in C to the n in which a point could go to infinity. So, for example, Rp1, this is an R together with infinity. I'd like you to think about this as being well, you can think about R as being a kind of straight line, but really gets kind of rolled up. So if you want to kind of identify a point in, so R gets kind of rolled up into the complement of a point in the circle, and then you glue on infinity, and infinity is the same as minus infinity. You can get to this point infinity by going either to plus infinity or to minus infinity in R. So the topological space, Rp1 is a circle, whereas Cp1 is C union infinity. This is a sphere, topologically, a two-sphere. Think about infinity here. Maybe 0 is at the bottom. You might have 1, I, minus 1, minus I, something like that. This is often called the Riemann sphere. I don't know if you've met it in complex analysis. So we call R to the n and C to the n affine space in comparison to the projective spaces Rpn and Cpn. So then, well, so somehow affine geometry, let's say in R to the n, it's kind of geometry invariant under the group GL of n R, but also extended by R to the n, where these are the linear transformations and these are the translations. So this kind of bow tie thing is something called a semi-direct product. It means a group is built from two other groups in such a way that the right-hand group is a normal subgroup, and that one is a quotient group. And it's a kind of twisted product, because the linear transformations are kind of acting on the translations. But you can see that there is a group of transformations of R to the n generated by the translations and the linear transformations, and that's the geometry we care about in here. So that's affine geometry won't come up much, but that's what the word really means. And there's kind of affine is a contrast projective. Okay, so why is projective geometry a good idea? Well, it's a fact that things are often simpler in projective geometry than in affine geometry. So you already know quite a lot of affine geometry. All the stuff you've been doing with lines in the plane and triangles and things like that and hexagons in school, that's really affine geometry happening in R2. And then there's maybe more geometry in R3. Just for example, in R2 we have a good notion of line, and two distinct lines meet in a unique point, unless they are parallel. Okay, so that's one of Euclid's favourite facts. In contrast, in RP2, two distinct lines meet in a unique point. Just full stop. There's no exception for the parallel case. And so parallel lines in R2 meet in a point at infinity in RP2. So you can see the affine geometry is being kind of contained inside projective geometry. And then you tend to have, when you've got a theorem in affine geometry, you have to add in some kind of exceptions depending on how whatever it is you're talking about is interacting with line to infinity. if you just forget about the line to infinity and work in the projective space, then you have fewer exceptions. As well, another example from later in the course, you could look at conics in RP2 or R2. So in R2, you can get ellipses, or you can get parabolae, or you could get hyperbolae. I'm really talking about, let's say, non-singular and non-empty conics. So in RP2, there's only one kind, which looks a bit like an ellipse. But then what you get in R2 depends upon how this conic is intersecting with a line to infinity. So for the ellipse, the line to infinity misses it. For the parabola, the line to infinity hits it at 1 point. For the hyperbola, the line to infinity hits it at 2 points, and therefore there's actually two chunks of curve in R2 corresponding to the two pieces of your hyperbola. Okay, so then the R2 cases depend on how the conic intersects the line at infinity. Okay, so at the cost of making things more abstract, we actually find that we get our theorems become kind of simpler. Okay, any questions? No? All right, in that case, let's move on to a section on examples of proofs in projective geometry. So today I'll give you a relatively simple but still non-trivial fact about lines in RP3. And tomorrow I'll give you a much more non-trivial proof. So let's now prove the following. So let L1 and L2 and L3 be lines, meaning projective lines, in the projective space RP3, which is P of R4, that do not intersect pairwise. So no two of these lines intersect. If you're making the same statement in R3, you have to say they don't intersect, and also no two of the lines are parallel. The conclusion is that then there are an infinite number of lines, in projective lines, L in P of R3, R4, that intersect all three lines, L1, L2, and L3. So the geometric picture is this. We're working in three-dimensional space. You can think of it like ordinary R3 with some points added at infinity. We've got lines L1 and L2 and L3, which are somehow skew. And actually we're going to see that you can get a whole bunch of lines like this. And actually there's, through each point of each of these lines, there is a unique line intersecting all three and passing through that point. That will come out of the proof. So we're going to prove a geometric fact. It's all about lines in space and how they intersect. But the proof is going to be using linear algebra, not in the projective space, but in the overlying vector space. And that's kind of characteristic of a lot of proofs in projective geometry, which is that you have some geometric fact, but you take it up into the vector space and you do linear algebra. So let Lj is a projective space of uj for j is 1, 2, and 3. So then u1 and u2 and u3 are vector subspaces of R4. And as these are projective spaces of dimension 1, the uj's have dimension 1 more, which is 2. So since L1 and L2 do not intersect, their intersection is empty, the intersection of u1 and u2, well, it can't be empty because vector spaces always contain 0. That's the only point it's allowed to include, because if there was a non-zero vector point in here, that would then the line generated by that point would define a point in L1 and L2. So u1 and u2 intersect in the 0 vector space. So hence R4 is the direct sum of u1 and u2 just by counting dimensions. So u and u2, they're two-dimensional vector spaces, they intersect in 0. Their span is a four-dimensional vector space, which has to be the whole thing, because that also has dimension 4. So let's take v in u3 be non-zero. So then, because u3 is contained in R4, which is this direct sum, we have that v is little u1 plus little u2, with u1 is in big U1 and u2 is in big U2, as u3 is contained in R4, which is u1 direct sum u2. Well, so if little u1 is 0, then v would be u2. So the point, square brackets v, would lie in both L2 and L3, which is a contradiction, because we've assumed that the lines do not intersect. And if little u2 is 0, then v lies in the intersection of L1 and L3, which is also a contradiction. So hence u1 and u2 and v are all non-zero. Also, u1 and u2 are linearly independent because they lie in vector spaces with no intersection. So let u4 be the span of u1 and u2. It's a vector subspace of R4. So then dimension of u4 is 2. As those two things are linearly independent. So little L4, which is the projective space of u4, is a line, a projective line in P of R4. All right, so we found ourselves a line. Also, L4 contains the point square brackets u1, which lies in P of u1, which is L1. And it contains the point brackets u2, which lies in L2. And it contains the point brackets v, which is u1 plus u2, and that lies in our line L3. That's what we chose. So L4 intersects L1 and L2 and L3. So it's not equal to the line L3 because it also contains u1, u2, which don't lie in L1, L3. Okay, so we found one line intersecting all three of these. So, by construction, there exists such a line L through any point brackets v in L3. So there are infinitely many such lines, because the map from points in L3 to lines is injective, and actually it's kind of surjective as well. There's the one-to-one correspondence, and L3 is infinite because your field R is infinite. So this proposition is also true over any infinite field, and that proves the proposition. Okay. Any questions so far? All right. Well, well, let me just say that we have proved a non-trivial geometric fact in a projective space P of V by using, well, linear algebra in the overlying vector space big V. And this is typical of many proofs in projective geometry. So you can get some mileage from being able to lift up from your projective space up into a vector space of dimension 1 larger. Okay, and next time we will talk about the proof of Desargues' theorem, which involves a exceedingly complicated diagram with lots and lots of lines in a plane. All right, if there are no questions, we can call it a day there.